This video describes methods for electronic spectroscopy, in which electromagnetic radiation in the wavelengths of ultraviolet and visible light promote an electron into a higher energy orbital. The spectrum ranges from shorter wavelength, higher energy ultraviolet light to longer wavelength, lower energy visible light. In this video, we'll briefly review electronic transitions and how these apply to conjugated polyenes. And then the video will conclude by briefly describing chiroptical methods, including determining the absolute configuration of chiral small molecules and the conformations of biomacromolecules, specifically proteins and nucleic acids. This diagram shows the ground state electronic configuration of trans-2-butenol, which involves 6 electron pairs, specifically the alkene pi bond, the carbonyl pi bond, and one of the non-bonded electron pairs on the carbonyl oxygen. Longer wavelength, lower energy light is sufficient to promote one of the electrons of a non-bonded electron pair into an unoccupied orbital. Shorter wavelength, higher energy light promotes an electron from the lower energy pi orbital into an unoccupied orbital. The following video will show the orbitals of the ground state of trans-2-butenol. This is the structure of trans-butenol in Spartan. The orbital labeled pi 1 has 4 p orbitals in phase from both the alkene and carbonyl pi bonds. The pi 2 orbital has the p orbitals composing alkene and carbonyl pi bonds out of phase, with a node of 0 electron density between alkene and carbonyl. The highest occupied molecular orbital, N, has non-bonded electron character on the oxygen. The LUMO pi 3 has nodes of 0 electron density at these carbon-carbon and carbon-oxygen bond positions. And then pi 4 has all of the p orbital components out of phase. At low energy light, 316 nanometers, the n orbital, minus 6.5 electron volts, has an electron promoted to pi 3 at minus 1.6 electron volts. On the other hand, higher energy light 218 nanometers, promotes an electron from the lower energy pi2 orbital at minus 7.4 electron volts up to the LUMO at minus 1.6 electron volts. In summary, lower energy, longer wavelength light is sufficient to promote an electron through the smaller band gap from n molecular orbital to pi3. Whereas higher energy, shorter wavelength light is required to promote an electron from the lower energy pi2 orbital into the pi3 orbital. This shows an actual ultraviolet spectrum for two unsaturated ketones, conjugated alkenyl ketones. The pi to pi star transition at lower wavelength also has a larger magnitude absorption band, whereas the n to pi star transition at longer wavelength, lower energy, has a weaker absorption band. For simple alkenes that are not conjugated to anything else, high energy light is required in order to promote electron from pi to pi star orbitals and see the relatively large band gap. On the other hand, for a conjugated diene, weaker energy, longer wavelength irradiation is sufficient to promote an electron from pi2, the HOMO, into the pi3 LUMO, representing a smaller band gap. In the mid-20th century, the Harvard chemists R.B. Woodward and Louis Fieser established that dienes that are fixed in an S-trans conformation require higher energy, shorter wavelength light for absorption, whereas dienes that are fixed in an S-cis conformation are promoted with lower energy, longer wavelength light. And this can be used to distinguish between these two isomers. More highly conjugated polyenes will absorb visible light. In the case of lycopene, which is found in tomatoes and other vegetables, absorption of the long wavelength light gives lycopene a bright red color. The bicyclic isomer carotene has additional substitution on the 11 conjugated alkenes, and this requires slightly higher energy, shorter wavelength light absorption, but gives carrots their distinctive orange color. A more interesting application of ultraviolet visible spectroscopy is optical rotatory dispersion using circular dichroism. You probably know that chiral non-racemic compounds will selectively absorb polarized light, giving lever rotatory or minus rotations, and the opposite enantiomer giving dextrorotatory or plus rotations. However, the sign of the optic rotation is dependent on wavelength. At a wavelength with the greatest absorption, lambda max, optical rotation is 0. But at wavelengths above and below the lambda max, the sign of the optical rotation may be dextrorotatory in one direction and levorotatory in the other direction. A circular dichroism spectrum that shows a dextrorotatory or positive rotation at wavelengths longer than the lambda max is said to have a positive Cotton effect. And this band has the opposite shape that then is a compound with a negative Cotton effect. This diagram shows the ultraviolet and optical rotatory dispersion spectra of camphor. At the lambda max, around 292 to 294 nanometers, the optical rotation is 0. At wavelengths shorter than 294, the optical rotation is levorotatory, whereas at wavelengths longer than the lambda max, the optical rotation is dextrorotatory. Therefore, this enantiomer of camphor exhibits a positive Cotton effect. The direction of the Cotton effect will correlate with the amount of molecular structure in the 8 octants of the space around the ketone chromophore. Placing the carbon of the ketone at the center of the octant, with the carbonyl coming out toward the viewer, then we can examine the 4 octants in the back. If there's more bulk in the back upper left or back upper right octants, then the Cotton effect will be positive. If there's more structure in the back upper right or lower left, then the compound will exhibit a negative Cotton effect. For applications of the octant rule, it is better to work with molecular models. This is a representative problem with 2 diastereomers of octalone. The transfused octalone 11A gives a positive Cotton effect, whereas the cis octalone 11B gives a negative Cotton effect with smaller magnitude. What matters is to evaluate the 3-dimensional conformation of the structure. For the trans bicyclic ketone, there's only one structure in which both of the 6-membered rings are the thermodynamically stable chair conformation. By examining the octant looking down the axis of the carbonyl, with everything now in back of the carbonyl, and here's the carbonyl oxygen in the octant rule, there is much more molecular structure in the back upper left. Therefore, the Cotton effect is positive. For the cis-fused diastereomer, there are 2 possible conformations. And These conformations will give different outcomes for the cotton effect. So we can actually use the evidence of the sign of the cotton effect, especially if we already know the fundamental stereochemistry of the structure, to determine what is the favored conformer of the structure. For the cis-fused bicyclic ketone, the conformer that is shown here with the methyl group axial relative to the cyclohexane on the right has more structure in the back upper right octant, consistent with a negative cotton effect. The other conformation would have structure in the positive octants, possibly partially offset by some structure in the negative octant, and would be expected to have a weak positive cotton effect. But instead, the cotton effect is weakly negative. I'll show this with models generated using Spartan. This is a transfused diastereomer 11A. I'll flip it as they did in the textbook. There is more structure in the back upper left octant. Here's another conformation, which is a simpler translation of the molecule. And there's more structure in the back lower right octant. These pictures are consistent with positive cotton effect. Now we'll look at the other diastereomer, the cis-fused 11B. We can look down the carbonyl axis, and we'll see that there is more structure in the back upper right octant, which corresponds to a negative cotton effect. Circular dichroism is used in a contemporary sense to analyze changes in conformations of biomolecules. This is an example of polylysine. At basic pH, the alpha helical conformation, which is the black curve, displays a negative cotton effect. The anti-parallel beta sheet conformation, which is 2, and the red curve, also exhibits a negative cotton effect, but it is a weaker cotton effect. And you can definitely see a difference in the shapes for conformers 1 and 2. What I find particularly striking is that at acidic pH, when all of the side chain amino groups of lysine are protonated, the protein adopts an extended conformation so that positive charges are further apart. And that extended conformation, which is the green curve 3, has a positive cotton effect. This has also been analyzed for naturally occurring proteins. Placental collagen, in its native form, has a triple helix form, and that is the dark blue curve, number 4, with a relatively strong positive cotton effect. But when the collagen is denatured, curve 5 now shows a very weak, if any, cotton effect. Here are 2 examples of secondary structure prediction. The protein lectin has an antiparallel beta sheet structure, but with a relatively unusual left-hand twist. And that shows up with a positive cotton effect. Whereas the trypsin inhibitor with an antiparallel beta sheet has the more common right-hand twist. The trypsin inhibitor exhibits a negative cotton effect. The last example involves the tertiary structure of nucleic acids. DNA typically exists as a duplex double helix. In the CD spectra on the left half of the slide, at pH 8.7, there is actually not that much structure in the CD spectrum. But as the pH becomes more acidic, we now see a strong positive cotton effect with the solid violet line. This is a result of protonation of one of these cytosines, so that there is a cytosine-cytosine base pairing. Note also in the pH inset at the top. At basic pH, there is not much absorption, which indicates that the bases, which are chromophores, are not base paired. But at acidic pH, the absorption now greatly increases, and that's consistent with a larger, more extended conjugation through hydrogen bonding through base pairing.